morning, everyone. Thank you for joining another edition of Storlytics Educational Webinars. My name is Sharif Abdurazik. I'm CEO and Principal at Storlytics Energy Storage. In this webinar, we'll be discussing an energy storage topic that's top of mind for not just developers, but also utilities deploying energy storage systems on a mass scale, namely best deployment strategy selection and optimization. So what you'll learn from today's session is how do you select your deployment strategy for your grid-tied battery system, what factors affect that decision, and how do you optimize whichever strategy you're moving forward with. So jumping in, we'll go over some housekeeping items in the beginning here. So first of all, this webinar is being recorded. By staying on, you agree to the session being recorded, and if posing any questions, you agree to these questions being public. Feel free to use the chat feature to pose questions. We'll address them as they come in. The Q&A feature is, for some reason, inoperable, so we'll be leveraging the Teams chat feature to address questions as they come in. Please make sure you're muted unless you have a question or something to add. In order for someone to really be unmuted, we actually have to do that on our end. So this request is mainly following your question or just your comment. Just be sure to go back on mute so we don't have any types of disruptions. Throughout the webinar, there may be pricing that is shown in the presentations or in the comments we make. Any pricing we speak about is purely illustrative and is not tied to any specific company. And finally, if you have any questions following this webinar, please email accounts@storlytics.net. So with that, I'll go ahead and introduce our esteemed speakers. So first, we have Dr. Bazzi from DTE Energy. He's an expert engineer working on the clean energy transition at DTE Energy, which is a utility in Southeast Michigan. Dr. Bazzi has over 12 years of experience in the areas of leadership, energy storage, hydrogen, emergent technologies, and applied artificial intelligence. He has a bachelor's and master's degrees in electrical engineering from the University of Michigan Dearborn and a doctor of philosophy in electrical engineering with a focus on artificial intelligence from Oakland University. Dr. Bazzi acted as co-chair, co-advisor in EPRI Program 71. He is currently the co-chair for EPRI's Program 221, titled Bulk Energy Storage, and serves on the EPRI Generation Sector Steering Committee. Dr. Bazzi supported a variety of research projects with EPRI and published multiple scientific papers and presentations related to battery storage, applied artificial intelligence, and multiple other energy generation topics. So, all right. So next, from EPRI, you have Jacob Rushkoff, who is a staff member for EPRI's bulk energy storage program. His role on the team includes conducting cost-benefit analyses for long-duration energy storage systems and vetting pilot energy storage system performance. Jacob will speak on developing a methodology for comparing more typical augmentation strategies with installing alternative AC connected long-duration energy storage technologies. And finally, we have Dr. Robin Bisht, who works for the battery energy storage and microgrid engineering team at Duke Energy and is leading the charge to deploy distribution and transmission tied energy storage systems across Duke Energy's regulated footprint in 6 US states. He is currently leading technical evaluations of augmentation and overbuild deployment strategies of grid-tied energy storage systems at Duke Energy. He received his master's and PhD from UNC Charlotte with a research focus on grid-tied inverter control and power quality. Dr. Bisht is the author of numerous IEEE publications relating to inverter control and renewable energy systems. He also holds a patent on utilizing UPSs for grid ancillary services. So with that, welcome to all our esteemed speakers here, and we'll just go briefly over the agenda. So we'll be starting off with a presentation from DTE Energy and EPRI, going over their joint work on optimizing deployment strategy of energy storage systems for DTE Energy. Feel free to pose your questions at any time. We'll try to get them in during the presentation, but if there are any left over, we'll address them directly after that presentation. Then we'll shift to a presentation from Duke Energy about their experience with augmentation, what they have seen from different OEMs, different integrators, and lessons learned there. So similarly, we'll be addressing questions as they come in through the chat, but if any remain, we'll address them at 12:20 to 12. Once we get to that point, we'll initiate the panel discussion, followed by attendee Q&A from all of you. So with that, I'll go ahead and pass it off to Tony with DTE Energy for the DTE/EPRI presentation. Tony, take it away.
Thank you, Sharif. All right, so sound check, can you hear me okay? All right, let's go to the first slide. I'd like to give an overview about our company, DTE. So DTE Electric is a subsidiary of DTE, and we serve around 2.3 million customers in Southeast Michigan. At DTE, we are committed to getting as clean as we can, as fast as we can, while taking reliability and affordability into account. So as you see on the slide, our Clean Vision plan is outlined, and that includes reducing emissions 65% by 2028, 85% by 2032, 90% by 2040, and ultimately reaching net zero by 2050. We have a clear line of sight to our target of 90% carbon reduction by 2040. And our Clean Vision plan, including, as you can see in the slide, expanding renewables, investing in state-of-the-art natural gas generation, while retiring our coal plants and promoting energy efficiency and demand response to reduce emissions. So retiring our coal fleet is a key part of our Clean Vision plan. However, we have to manage that very carefully by working with our communities and our employees as well. So in May 2021, we retired our River Rouge power plant, followed by St. Clair and Trenton Channel power plants in May 2022. Bell River power plant will be converted to a natural gas peaker by 2026. And the whole of Monroe power plant will be retired by 2032, ending the use of coal at DTE. Expanding our renewable portfolio necessitates the need for energy storage. So as you can see in this slide, we have a target of 1,830 megawatts between 2033 and 2042. The first tranche of energy storage deployment will be available by 2025, followed by 120 megawatt in 2027 and 430 megawatts by 2028, and around 1,050 megawatt between 2033 and 2042 or 2042. So collectively, it's around 1,830 megawatts worth of storage. So our first deployment is the Slocum Battery Energy Storage Peaker Replacement Pilot Project. It's a 14 megawatt 4 hours pilot, lithium ion. So that would be around 56 megawatt hour worth of storage. It's currently in design, transitioning into construction. It targeted in-service date is the end of the year. And you can see the rendering, how the site used to look like, the peaker site used to look like, and how it's looking like right now in the picture on your right-hand side. This project is eligible for IRA benefits under the Inflation Reduction Act. And this project will be the reference case and the baseline for our future deployments because it will allow us to learn about engineering, operation, cost, and feasibility experiences. Our second project in the pipeline is the Trenton Channel Battery Energy Storage System. It will be called the Trenton Channel Energy Center. The Trenton Channel Power Plant is undergoing demolition. This is how it used to be. You look like in the picture in the rendering of how the project will look like. As you can see, the future state of the project on the slide. It's going to be a 220 megawatt project for 4 hours, lithium ion again. So that will give us around 880 megawatt hours worth of energy storage. The use case will be, grid reliability, arbitrage, peak shaving, flexibility benefits, voltage support. It's targeting in-service operation first quarter of 2026, and also it's eligible for IRA benefits and also the energy community adder as well. Moving on, this year we established a cross-functional team in collaboration with the Electric Power Research Institute to look at the augmentation strategy. And the first step we took as part of this cross-functional team is to establish our strategic priorities that will govern our deliverables. And that includes, of course, safety, followed by reliability and availability, and then flexibility, and ultimately cost. So we put our agenda for the year as part of the cross-functional team. The first step we took is identifying the different scenarios for augmentations. Then we contracted EPRI to look at to evaluate these scenarios using a data-driven approach. We also conducted benchmarking sessions with our utility peers. We're looking to summarize the analysis, recommend the optimum strategy, and develop the implementation timeline, issue the recommendation to leadership, get some feedback, refine our strategy, finalize. And the most important part of the strategy, given the technological uncertainty around lithium-ion batteries, especially around cost and technology development or rapid development, that strategy needs to be refreshed on a periodic basis. So the scenarios we're looking at to offset degradation through the process of augmentation include, first of all, the reference case. This is where we're looking at the OEM recommended augmentation schedule. Then removing the constraint around the 1 cycle per day with and without, looking at more frequent augmentations, so more project. So let's say the schedule currently is augment every 4 years. We're looking at augmenting every year, every 2 years, every 3 years, even every 5 and 6 and 7 years. So we're looking at the sensitivity there. Also evaluating initial overbuild to offset degradation, a mix between DC and AC augmentation, and augmenting the lithium-ion technology with parallel LDES technology that Jacob will cover in details. So the baseline for these scenarios, as I stated, the first step is to look at initial overbuild, and that means, adding extra capacity at day 1 to offset degradation, whether it's for the first 5 or 10 years or for the lifetime of the asset. The second part, DC augmentation, is where you're adding energy segments to the existing arrays. The third one is AC augmentation, where you're going in parallel to the existing array. And the last baseline is a different technology, whether you're augmenting parallelly or in parallel with these arrays, utilizing an LDES technology, for example. At this point, I'll hand it over to Jacob Rushkoff from EPRI, where he's going to cover the data-driven approach and a detailed overview of the LDES technologies that we're currently evaluating as part of our augmentation strategy. Take it away, Jacob.
Thank you very much, Tony. You all can hear me? All right. I appreciate the introductions. So as y'all have heard, I'm with the bulk energy storage group here at EPRI, and so I'm really quite particularly interested in all these LDES technologies, and I think it's an interesting and novel idea pairing long-duration energy storage with lithium-ion and using these kinds of augmentation steps to kind of to shift the energy storage strategy with different conditions, whether they be through the electricity market or different needs that you need for longer duration, greater reliability. So some of the technologies that we're investigating in this study as pairing with the lithium ion is considering compressed CO2 energy storage. This is similar to compressed air in the sense that you're storing liquid CO2 and the heat of compression just to compress that CO2, and then using the compressed CO2 in a turbine with the heat released by TES to generate power. In addition, we're looking at adiabatic compressed air energy storage, very similar to the compressed CO2 in the sense that you're compressing air, with the exception that instead of liquefying the air, like the CO2 is liquefied, the air is stored as compressed gas underground, typically. In addition, we're also looking at pumped heat energy storage. This is essentially like a heat pump during the charge process, where the heat pump generates a hot reservoir and a cold reservoir, and then discharges using those two hot and cold energy storage to drive a heat engine. This can be done with air, this can be done with CO2, whether it's a closed Brayton cycle, a supercritical CO2 cycle. There's really quite a few technologies going into this. And lastly, we are also looking at vanadium redox flow batteries. And this is arranged in a similar way to other flow batteries, where battery pumps liquid analyte and catholyte into adjacent cells where protons are able to migrate across that membrane between the two cells. But first, I wanted to cover how we developed this reference case, because that's going to be quite important for how we compare then to installing long duration energy storage. So I'll be going over this flow sheet here, this workflow, where first we start with modeling the desired operation of the battery system. So we do that here using EPRI's distributed energy resource value estimation tool. We all call it DERVET. We never use the whole name. But what you can see here is the tool itself takes in LMP, or locational marginal price data, over a full year. It takes in battery constraints and battery performance, such as round trip efficiency, self-discharge rate, the power and energy capacity. As a result, it produces this power dispatch profile. Essentially, what is going on here is along the x-axis, we have the model stepping through different days throughout the year. And then along the y-axis, you have hours in a day. So at the very top of the graph, you have the morning. At the bottom, you have the evening. Then left to right, you have January to December. And so then each of these pixels in this chart is showing what is occurring at that hour, whether the battery is charging, whether it's idle, not doing anything, or whether it's discharging, yellow being discharging, purple being charging. So something interesting, an interesting characteristic here is just that you can see during the summer you have that one peak in the evening, and then in non-summer months we have a double peaking. So this is an interesting use case where when we're talking about like how many cycles can a battery do in a given day, this rule has certainly come up when we ask questions like, does one cycle mean charging, discharging half of it, charging a little bit more, and then discharging again? And so that's essentially the definition we go with. So that dispatch profile, and of course the revenue that comes from it, will be important. The revenue, when we finally get to the last components like the net present value and internal rate of return calculations, the dispatch profile is important for then putting in as input to the Storlytics model. So here we're using Storlytics to model the degradation of the battery, how we would like to use it. In addition, other inputs to the Storlytics model, and I'm sure given this is a Storlytics webinar, hopefully some of you are familiar with this. You can input weather data, the battery model data, so cell specifications, module specifications, to then produce what might be a realistic view of battery degradation. So using Storlytics, now I'm just showing you like a generic battery model. not show out all this data before you're finished with the study. So, but using Storlytics, we developed this degradation profile. And so we get a state of health of the installed batteries over the 20-year life. And then we can use that information to decide when it's best to install more stacks, more battery stacks. So then this last step here is bringing the results of these two softwares kind of together. First, Storlytics out, so that degradation profile that we produced goes into an augmentation model and then cost model to determine when we should be installing, and I'll show you what that looks like. There we are. So you can see this red box has that same state of health profile we generated. This is, again, I should stress, this is the generic model. This is not necessarily reflective of the system we're studying. But we have this nice spreadsheet where we can then include additional steps in battery augmentation. So you can see here, I'll just try to guide you through this spreadsheet. Check the time. All right, we're so good. So for these first two columns here, where you have BESS 1, this is the initial installation of a 100 megawatt hour system at 4 hours. So you can see the 25 megawatts. And then we note that, let's say in this case, we're trying to make sure we're staying above 90 megawatt hours. And so year one, we enact an augmentation step, adding in an additional 10 megawatt hours. And you can see this 10 megawatt hours is degrading, given the same degradation profile as we generated from the first battery system. It's degrading in the same way, but just offset by a year. And so then the same will be true of this battery 3, 4, 5, 6, and 7 augmentation steps, where they're being installed later in the project life. And so they're shoring up that energy capacity roughly up until the end here. We have it's reaching this 88.2 megawatt hours. And so everything is aggregated here on the right side, where you can see the energy capacity, the power capacity, some nice graphs to see how that's progressing over the project life. So then after figuring out how we want to do that augmentation and trying to optimize, and as Tony said, going through different scenarios for these levers that we can pull to adjust these augmentation strategies. We then take all the costs associated with augmentation. We take the costs, of course, associated with the project itself, like the initial installation, the revenues from dispatch modeling, including, so this would be arbitrage revenue, could be ancillary services, capacity payments, and then also we grab some auxiliary power costs as well. All this comes in to calculate key performance indicators. In particular, we're focused on net present value and internal rate of return, which don't always agree. I think it's interesting to, in a project in and of itself, take a look at these different indicators that you could optimize a project for. We are also calculating levelized cost of storage, but we tend to prefer net present value in this case.
Hey, Jacob, quick question posed here by Karthikya. What is the advantage of augmentation in year 1 or 2 versus overbuild? And he continues, I would have imagined augmentation would happen after a few years.
Yeah, that's an excellent question. And this is something that we're going to be studying through our efforts in this study. I'd say what we're working on is still rather preliminary, so I wouldn't comment on what is the best strategy. Essentially, I think there's some value to installing early because you're going to run into a lot of degradation early. That's essentially why you see more frequent installations early on to this project, because that's when a large component of that degradation is happening. Of course, an easy counter would be, well, why not just overbuild, and then you'll shore up your capacity and you won't have to go through an additional augmentation event. I think that's a fair question. So that's something that we want to study.
Got it. So in other words, this is kind of a step in the analysis, but not necessarily the optimal solution. So you're kind of going over kind of the steps you went through rather than kind of the final result. Okay, makes
Absolutely.
sense.
Absolutely.
Yeah.
Yeah. All the
Thank you.
results that you see here are using generic data for battery energy storage systems. And this augmentation schedule is in no way characteristic of any system that we've been studying. This is simply to show the process or how we develop that reference case.
Thanks, Jacob.
Yeah, I appreciate the question. All right. And then something I want to cover here then is how we're going to go ahead and try to compare installing LDES technologies. So this is those 4 technologies that I talked about previously. We want to see how we could install those in parallel with lithium-ion batteries in order to maintain that total energy capacity. So here you can see in a very similar process, we're installing LDES instead of installing more battery stacks. And something you'll notice is that this energy capacity is not changing over time. That's not always true with LDES. You know, there's still some electrochemical batteries that we're going to be considering that are expected to degrade over time. But these are being installed in parallel with the battery systems. Now, something to note here is that we are installing 10-hour batteries. So you can see 20 megawatt hours at 2 megawatts. And so while you're maintaining energy capacity, that doesn't necessarily mean that that energy capacity can be utilized by the initial power capacity. It would be constrained by this 2 megawatts or then 4 megawatts in the future. So that's something that impacts the dispatch modeling. It's something that impacts, you know, how we total up this cost benefits and should be considered when you're thinking, okay, well, what do I want my system actually to do? How do I want this to behave in the market?
So quick question, Jacob, and this one's coming from me. So was there an energy duration requirement at the POI for this project, or was it kind of just an energy requirement? How did EPRI and DTE go for the decision on or power capacity augmentation for the system?
So this system is going to be playing into MISO. And so something that you have to keep in mind is if you want to participate in the capacity auction, that comes with a requirement for meeting a 4-hour minimum duration. And so the goal would be that the system has capability to meet that minimum duration. Now, I think there's a good question to be had that if we have this hybrid energy storage system where we have lithium ion and long duration energy storage, what does that mean for playing into the capacity market? That's something that we need to study and better understand. But yeah, we are currently looking at this as a 4-hour system that we want to maintain that 4-hour duration.
Got it. Okay, perfect. Then another question we got from Rajat. Does the output from Model 1 represent the battery profile based on the use cases we select? Also, how are we selecting the size of battery? And I think what Rajat may mean by Model 1, and Rajat, please correct me if I'm wrong, is Dervet, if I'm...
Oh, so in Dervet, and I guess this kind of links to your previous question, in Dervet, we are modeling the storage systems as 4-hour energy storage. And so in Dervet, we maintain that 4 hours and we don't allow the energy storage system to, if it has, you know, additional capacity, we don't allow it to bid that additional capacity essentially. That's in the case where we're just looking at the 4-hour like reference case for lithium ion. As we're installing LDES, we actually run these as 2 separate models. And we just ensure that the POI is accepting that total capacity. When I say POI, I mean the point of interconnection, allowing that to remain at the max export.
So in other words, Oh, go ahead. Go ahead. Okay.
No, yeah, go ahead.
So if I understood you correctly, so you're using Dervet to kind of find the optimal or the dispatch at the POI that would maximize the value to the grid or maximize revenue from arbitrage, right? As far as the grid is concerned, so you're not worried about the battery. And then once you have that dispatch profile, then you're using that to find, right, the specifications of the battery system, right? So how much overbuild, augmentation. So now you basically have a defined dispatch profile to base your energy storage system on, afterwards, using Storlytics. Okay, got it.
Absolutely. And that dispatch profile, I mean, so that's something that we're going to be studying as well, is essentially how much you're going to allow the system to cycle in a given year, because that is going to deeply impact degradation, but it's also going to impact how much additional revenue you can gain.
Yep. Interesting. And a follow-up question from Rajat, and really it was occurring to me as well. Is Dervat solving for just arbitrage opportunities, or is it also looking at other ancillary services? Like, in MISO, there's this new fast ramping resource market and these other services.
Yes, we are also looking at ancillary services. We started out just looking at arbitrage. And I think that comes from the idea that ancillary services don't make up that large of a capacity that's required. But ancillary services, will certainly make up a considerable portion, at least initially, for battery revenue. And so we're stacking these services. So we take historical prices for LMPs, we take historical ancillary service prices, and we co-optimize the best strategy for the battery to take. The dispatch profile you see below, that is not including ancillary services, so you might expect a lot more variation as opposed to just remaining at the maximum charging and the maximum discharging capacities in the case of ancillary service bidding. Questions?
I think we are good with questions at this point. So
I guess real quick, I think I forgot to mention that Dervet is an open source software, so you can download that and use it if you guys are interested. That's just dervet.com. To see that methodology in more detail. All right. Well, good talking with y'all. Happy to
all
hand
right.
it
Well,
over.
thanks, Jacob, for that. Very, very informative. I wasn't sure if you had any additional slides, so I apologize.
No.
Greatly appreciate that overview. Really interesting work, and I really like the methodology kind of EPRI and DTE Energy are applying. I think in the energy storage industry, more than often, there tends to be generalizations around the characteristics of and performance of different energy storage technologies, lithium among them. And, we tend to assume that a single technology will perform in the exact same fashion with the exact same degradation, regardless of use case, regardless of temperature, regardless of location, regardless of number of cycles, depth of discharge, things like that. So the way EPRI and DTE Energy are going about it, kind of getting the use case defined, getting the dispatch profile defined, and then solving for the size of the energy source system, the degradation. And I know we talk a lot about degradation because it's important, but also the energy losses, the dispatch losses. Like if you talked about a long duration energy storage technology. So if you're employing an LDES, right, that has higher self-discharge, right, what's going to be the overall energy losses over the project lifetime? That really matters, and we're starting at Storlytics here to see developers kind of feel the burn of underestimated energy losses over project lifetime. Like you have folks at year 3 and year 5 of the project life, and they're looking at the amount of energy they're losing per year, and wondering why it's so much more than what they estimated. Well, it's because energy storage systems are very dependent on the use case and dispatch profile. So definitely EPRI and DTE are going about it the right way, in my opinion. So again, thank you, Jacob, for that overview, and thank you, Tony. Very, very interesting project there. So with that, I'll go ahead and pass it off to Dr. Robin Bisht of Duke Energy. You know, Duke Energy's definitely doing a lot on energy storage, operating in 6 different states. It seems like every other week we kind of hear about a new project Duke Energy is deploying. So very interested to learn about lessons learned at Duke Energy. So Robin, take it away.
Yeah, thanks, Sharif. Am I audible?
Can you hear me?
Okay, all right. So yeah, that was an amazing presentation, by the way. That was very detailed work. I'm
Appreciate
actually
it.
pretty blown away. What I wanted to kind of add to this conversation is some of the initial thoughts we are having on augmentation for the projects that are coming in really quick at Duke Energy. And what are we thinking about pros and cons for overbuild versus DC augmentation versus AC augmentation. So I wanted to kind of give a brief about what we're thinking right now for all the different strategies and where we are at Duke Energy. So the current goal for Duke Energy is to achieve 70% reduction in CO2 emissions by 2030 and complete carbon neutrality by 2050. So in the grand scheme of things, energy storage definitely plays a very important role in kind of achieving that for Duke Energy. In the portfolios, and this is public information.
Hey, Robin.
Go ahead.
Hey, Robin, sorry for the interruption. Can you hit hide on that
Sorry.
message?
Yeah.
Yep, so that,
Yeah.
perfect. Thank you.
Sorry about that. So yeah, in the grand scheme of things, when we are developing our portfolios on how the overall carbon neutrality would look like, you can see that standalone battery energy storage is up there. So we have around 1.8 to 2.1 gigawatt installations by 2030, and even higher by 2035, reaching about 4.2 gigawatt of standalone storage. In the new solar section, you do have solar plus storage as well. So you have some more storage over there in the portfolios that we're considering for Duke Energy. So moving forward, we'll be having a lot of projects coming in. What I wanted to do is first go through the benefits of battery energy storage and what the use cases we are considering for our overbuild scenarios and our augmentation, potential augmentation, and then kind of break down the overbuild strategy and the different flavors of augmentation strategies that are out there. We've been speaking to a lot of vendors to get some insight on what our industry peers are looking at and try to weigh the pros and cons of the different strategies that we've heard about and moving forward from there. So right now, I think, as we've already discussed, energy arbitrage is one of the major benefit that we're looking to tap into. Obviously, Jacob gave some insight to that. The other thing that BESS would be helping us out is kind of the renewable energy integration and smoothing the intermittency, providing capacity firming. So battery energy storage is going to significantly contribute towards that. And if we talk about grid stability, we're also looking at frequency regulation. As Sharif mentioned, there is more and more requirement for frequency regulation and voltage. Like we know, inverters are free reactive power. The switching component in the power electronics basically provide that benefit. So these resources are going to be really valuable for reactive power consumption and injection that can provide additional voltage support. And obviously making the overall market more reliable. So that's kind of the use cases that we've been looking into. Primarily our current portfolio or current projects that we have, both distribution and transmission tied. And frankly, augmentation kind of makes sense if it's a bigger battery, transmission connected battery. I handle both distribution and transmission connected projects. So overbuild strategy is basically what we've been doing right now. It's simple, it's effective. You have peak demand from day one, which kind of helps most of the industry to tap into or get to that carbon neutrality faster, because that's what the main goal is for everyone right now. So this particular strategy is useful for utilities that are expecting significant growth in energy demand. You have asset deferral, you have generation replacement. So if you have generation replacement requirement, Overbuild strategy can provide that day one. Certain flavors of augmentation can also provide that, but Overbuild being just a simpler installation just helps with that. It simplifies operation and planning in the grand scheme of things. The need for frequent upgrades, the one thing that when we were thinking about creating the what an augmentation strategy would look like was to align constructions with upgrades and whole sort of bunch of things. Overbuild just kind of does not require all that. You're just building on year zero and you just have the regular maintenance that you have to worry about. It simplifies the interconnection. It does not require re-rating of the facilities. Peers in the utility would know this. Interconnection packages are a huge pain. So going through that process is minimized with just a simple overbuild strategy. And overall, most often or not, we don't talk about it. It's an easier contracting framework. We don't have to jump through a lot of hoops. So it just makes everything so much more simple. Cons, obviously, you have a huge capital required at the front end, right? That's one downside to an overbuild strategy. One of the things that we looked at is the underutilization of extra capacity during normal and low demands. Basically, you're overbuilding this battery project. It's installed at year zero, and during low demands, you're not using all the juice, all the megawatt hours that you've installed. So sometimes there are chances that you might not be utilizing your facility to the maximum potential. You're locked in to the cost of technology at that time. Augmentation kind of gives you that flexibility. So it really comes to the cost. If that matters, this Overbuild strategy might not be the best case. Can lead to inefficiencies and higher operational cost per unit of energy storage, energy stored, similar to point number 2 in the cons that I've mentioned. So what are we looking at right now?
So Robin, I want to dissect a bit a point you mentioned on the previous slide. So, one of the pros of Overbuild, right? You mentioned the interconnection advantage of, as opposed to AC augmentation, where you kind of build into your POI capacity, right? You're kind of utilizing your full interconnection capacity from year zero.
Yes.
So that's definitely kind of an acknowledged advantage. But given kind of EPRI and DTE Energy kind of presented on an AC augmentation strategy, I wanted to put this question to Jacob and Tony regarding their plan on that front. So from what we've seen in kind of the past is folks who kind of are planning on an AC augmentation strategy, they already have their interconnection capacity set, and they kind of build into it rather than they utilize that augmentation capacity in the first deployment and then are putting in other interconnection requests. So Jacob, is that the case, and Tony as well, is that the case for DTE Energy? Do you already have that interconnection capacity reserved and growing into it, or are you planning to submit additional interconnection requests to attain that capacity in future augmentations?
Thank you for the question. I mean, we're going to be operating in the bounds of the generation interconnection agreement. for the specific site. So in case, for example, if I take Trenton Channel Energy Center, it's a given the GIA will be 220 megawatts. So obviously we can't inject more than that. But just commenting on Overbuild is interesting what Robin is presenting. And we've benchmarked with Duke before and others. What we see out there is for the smaller systems, smaller size systems, capacity wise, seems like the Overbuild is being considered as an initial augmentation step, initial overbuild for the first 5 years or the first 10 years, whichever the case may be. But we're still performing, our due diligence to finalize our strategy and compare that as well against AC augmentation in other scenarios, like I presented there. So more to come. The results will be presented in the EPRI membership. If you're an EPRI member, you'll be able to get your hands on the results, and then we're looking to publish those maybe through an IEEE conference. And obviously for the folks that are following you, Sharif, they will probably do another webinar where we can go over the results, at least what makes sense for us given our projects currently and into the future.
Perfect. Really, yeah, really interesting work. Can't wait to see the results. Right. All right, yep. Robin, back to you.
All right. Yep. Yeah, that was a great point, Sharif. I'm glad you stopped me. So we were looking at the overbuild strategy, and basically what we are seeing in some of the proposals coming to us, where the overbuild ratio is at right now, because you kind of have this huge battery facility come in at year 0, and how we are defining the overbuild ratio is what is required, what is at the beginning of life at the battery terminals to the required end of life POI energy. So right now the overbuild ratio, what we are seeing is 1.5 at the lower end to 1.65 on the higher end. 1.65, I think it was a few years back where, it was, I think, earlier technology. Right now, as technology moves forward, it becomes better. You see this overbuild ratio kind of going down because you have better TE equipment efficiencies, right? So overbuild strategy is definitely going to improve as we move forward and as technology develops. Augmentation. So the way, and I feel like there are different flavors, so many different flavors of augmentation. The two that right now what we are focusing on and what we are seeing out there is phased implementation and flexible deployment. Flexible deployment is basically, I think, adopted by, industries with not a significant capital. So flexible deployment kind of suits their style of augmentation, where you adjust the capacity as needed for augmentation. Phased implementation, you have a plan for different phases as what was presented previously. So these are the two, I think, more dominant augmentation strategies that we've seen out there and what vendors are proposing. And some of the pros and cons for augmentation in general, what we identified is obviously support for renewable integration. We have a really high solar and wind installation within the Carolinas, so that's going to help us. Deferred capital expenditure, obviously, like we discussed before, overbuild requires a huge initial capital. Augmentation kind of relaxes that. You can defer the initial capital to later on when you have the augmentations coming in. Adoption of new technologies. This can be a pro and a con, because if you have different technologies for augmentation, it just, the control architecture and everything becomes so much more difficult. So we need to keep an eye out on what new technologies are coming in and whether they can work well together with the older technology, and we can augment it correctly. So it is definitely, if that works out, it is definitely an advantage for augmentation. Adaptive capacity, and as like I said, as adoption increases, the costs of AC and DC coupled systems are likely to decrease over time. So augmentation would definitely be helping with that. Cons, I think we all know it's definitely very complex in planning and coordination. I think we are already seeing a lot of studies as to when the augmentation cycle need to be, how do we align it. And we have a case study at the end of the presentation where we tried coordinating it for a particular project. I'll go through that and we can talk about more there. Coordination with utilities. So you need continuous engagement with utilities to update the interconnection agreements and grid impact studies. So that's one con for augmentation, because as you are adding more inverters to the existing facility, you need to possibly you have to update the interconnection package and maybe have some restudy done for the facility. So that's another pain point for augmentation. Installation upgrades, temporary disruptions, obviously during augmentation, addition of new capacity, component upgrades are another thing that we are considering and we need to consider when we are talking about augmentation. And securing funding, right? Like, I think one of the things that we don't talk about is justifying augmentation, right, as an investment. So securing funding might be difficult for augmentation projects. Maybe there's a person out there that disagrees with the point, but right now that's what we're seeing is justifying the investment for augmentation. Overbuild is heavily considered as a much more safer route for utilities right now.
So, Robin, just a couple questions here. So we have one question kind of about, I'll just read it out. What is the general rule of thumb for initial beginning of life overbuild? And I'll kind of expand on it a bit. So how is Duke Energy kind of going about finding the deployment capacity, the energy capacity for each phase of augmentation? If you're planning an augmentation or if you're planning an overbuild, how are you going about finding that kind of overbuild ratio?
So yeah. So I think early on we were heavily relying on the degradation curve provided by the vendors themselves. Generally, those will be 1 cycle a day degradation profiles, not specific to maybe a dispatch profile that we provide. So initially we relied on that. Currently, we are using tools like Storlytics to kind of identifying that beginning of life capacity. We have past project experiences on the system losses and what the aux requirements would be. So there are some few assumptions there, especially on the aux load requirements, but and system losses. So we add some conservatism into our estimates for system losses, equipment efficiencies. Well, equipment efficiency we usually get it from the vendor, but stuff like transformers are definitely an assumption. So we add some conservatism in there, and that's how we get to our beginning of life battery terminal capacity. And then again, when we go out for our purchase orders, we add them to our contracting framework. But right now, I think we are leveraging Storlytics to help us out with that.
Got it. And one thing I want to kind of mention about that question is kind of posed as, what's the general rule of thumb when it comes to beginning of life overbuild? And the question goes on: is it 15%, 20%, 25%? I guess my comment back to Andreas, who posed it, given kind of Robin's response and what we've seen from EPRI, is that it really makes quite a difference in project finances what your estimation on degradation and as a result overbuild ratio ends up being, because lithium battery cells are not cheap, right? Today we're talking about let's just say $250 to $300 per kWh or so. If you look at kind of overall project finances, that ends up being, I mean, conservatively speaking, probably more than 50% of the cost of the overall project. So being off by 5% is really, really impactful. Being off by 5% in terms of degradation or overbuild ratio is really, really impactful to project finances. That's why it's using rules of thumb in this particular point is really, really dangerous. All right, so moving to, we have another question here, and I think this one is probably for Duke Energy and DTE Energy as well. Is there any effort to simplify interconnection agreement or material modification amendments for AC augmentation from the utilities perspective, primarily for storage systems where the intent is to keep the power capacity the same?
Yeah. Well, I haven't heard any, well, if there are any improvements. I don't know if there, I don't know, I'm not sure on that. I don't think there are any improvements. I think material modification, as per my knowledge, has remained the same. And Sharif, you've been at Duke Energy as well. I think more or less the requirements have been the same. I don't know about DTE Energy, if they have any comment on that.
Yeah, go ahead, Sharif.
Go ahead.
So,
No, well,
from
I was just gonna say it feeds kind of into like the what we discussed about for AC augmentation, planning on growing into the capacity that you already have approved as part of the interconnection, rather than doing it through like an interconnection agreement amendment. Because I mean, when an interconnection amendment is considered, it's definitely almost in all of the cases I've seen, and Tony, kind of interested to get your feedback as well. Adding inverter capacity is definitely a material modification. So yeah, from my perspective, I think it's probably best to already to plan to grow into an already accepted or approved capacity rather than amending it, because I think it's very easy to trigger an upgrade that is may very likely be cost prohibitive. So kind of making an augmentation phase reliant on an interconnection amendment, from my viewpoint, is a bit risky. But Tony, kind of interested to get your thought as well.
Yeah, I mean, like I said before, we're going to be operating by the bounds of the approved interconnection agreement. And when we augment, we're going to augment to that approved capacity to be able, for example, to maintain that 220 megawatts from one of the projects that I talked about, rather than trying to go over that, at least at this point.
Perfect. Thanks, Tony. And I guess something to mention here is that I think it's probably true for Robin and Tony as well. Much like any other developer, even though they're both kind of with the utilities, but when they're developing projects, they need to submit interconnection requests like any other developer. So they're bound to kind of the same rules there.
Right.
All right. So thank you for that question, Sanjay. With that, we'll kind of get back to Robin's presentation here. And so Robin, I'll pass it back over to you.
Okay, yeah, thanks. All right, so I think I was at the AC and DC coupled topology. So I know we're all pretty familiar with the AC and DC coupled topology for augmentation. AC coupled topology is basically adding inverters and new battery racks, which tend to be technology agnostic. Basically, you can add new technology as it comes, and it's a simpler augmentation style because you're not disturbing any of the previous older builds, and the integration is much more easier than compared to other augmentation flavors where you are on the DC side of things, where you have to worry about the short circuit capacity of the DC bus of our inverter, and how many you can't connect an infinite number of battery racks behind the inverter. So AC topology is considered to be more flexible in the system design, has a simplified control and overall integration. And one of the points that was brought up in our internal discussions was the older builds remains untouched. One thing that gets lost in the augmentation conversation is when you are trying to augment on the DC side, more often than not, in the flavors of augmentation, you are kind of either rearranging cells or adding to the existing system, and you are kind of touching things, and it's a more intrusive method, where the older systems are kind of dismantled or changed, that can cause a lot of mishaps and equipment failures. So when talking to our project management crew, that's one of the concerns that they definitely voiced, where in AC augmentation, you're leaving the older build untouched, and that is a much more cleaner augmentation than looking into a DC augmentation where it's more intrusive, and more often than not, like when you are touching existing systems, things have there are a chance to for things to go wrong. But in the AC coupled augmentation strategy, you're obviously derating. If you have a fixed capacity in the interconnection agreement, you are derating the older inverters so that you don't go above the megawatt capacity for that project. You do have a relatively higher initial capital requirement for this. It's not modular in nature, well, at least for now. I think more and more as we go down the road, we're looking into having string inverters come back in for on the battery side. So that would be, I guess, down the road, a much more augment friendly topology where you have modular battery systems that you can augment, and not having just one big central inverter and connecting a bunch of battery racks behind it. Multiple inverters for AC topology, you're increasing a lot of power quality issues. This is not often talked about as well. You have higher harmonics introduced onto the battery facilities. And with different inverters coming in at different phases of augmentation, you have different maintenance schedules. So that gets kind of tricky.
So Robin, that's a really interesting point. Can you kind of expand a bit on the harmonics issues?
Right. So inverters have larger filters. Most of the times you have big inductors, capacitors at the output terminals of the inverter. So if you keep on adding a lot of inverters at the same AC bus, there is a chance of like having a really high resonance at different frequency points that could lead to higher harmonic current injections on the AC side. And there was this really great presentation from a power quality engineer at Duke Energy that actually was the first one to notice that, hey, the harmonics is definitely an issue at one of our older sites that is often not talked about. Again, at least on the industry side, I think on the academia side, there are a bunch of literature available that inverters, and especially when you increase the amount of power inverters in a tight space, I guess, you have problems with harmonics because of the series and parallel resonance in the system.
So as it relates to kind of this topic, are you talking about like the risk of higher harmonics or harmonic resonance resulting from the use of smaller string inverter units, or in general for AC augmentation as you add more inverters, regardless of their capacity or unit capacity, rather?
Yeah, regardless of their capacity, you're adding more. And if they're string inverters, if they are central inverters, string inverters, you can really, really optimize the amount you augment. Central inverters, you can't really optimize as much because you have a big chunk of a megawatt that you're placing in to the augmentation, whatever augmentation that you're planning for. But nevertheless, you're adding inverters, so you're adding more power electronics devices, LC banks, and that causes some power quality issues that we usually don't talk about.
Got it. Okay. Let me take some questions from the audience here. So Francesco Berman posed a question here. What is a general dispatch efficiency for a BESS connected at high voltage, so transmission tied, for example, not considering depth of discharge, just the system efficiencies? And I think probably for the audience, it'd probably be good to provide something kind of taking into account auxiliary load and not taking it into account, and also the dependencies there. But go ahead. And this is for you, Robin, as well as anyone else who wants to chime in.
Yeah, that's a good question, but I feel like I would need to probably take out my calculator or write off the top of my head. I don't think I'll be able to answer that with an exact number, like what is the round trip efficiency without the depth of discharge, without certain auxiliary losses. I think it's just a very difficult question to answer. I don't know if anyone else has any insight on that, or maybe I'm not understanding the question in its entirety. I don't know.
Yeah, so I think, I'll kind of attempt it, and definitely, feel free to chime in. It is dangerous to kind of apply, these rules of thumbs, these general quantities. But at the risk of breaking my own rules, I'll just kind of give a high level number, and I'll try to be as specific as possible as it relates to the conditions that are underlying in this number. So typically, a lot of people use 85% as a general round trip efficiency for lithium systems. Based on our simulations and analytics, that is only true for single cycle a day applications in a moderately temperatured or meteorological location. So think, North Carolina. Definitely, if you're, deploying a battery elsewhere with much higher temperatures, you may get less than that. And also, if you definitely change the dispatch profile or the type of profile. So in other words, if it's short energy pumps or deep, versus deep discharges, so shallow discharges versus deep discharges, controls kind of the losses and also the auxiliary load being consumed. So I hope that helps.
Yeah, that's that's a really great way to put it, Sharif. I think I agree with you. There's so many moving parts. Like, how would you like? Yeah, I wasn't even begin to like attempt to answer that question because there's so many moving parts in kind of knowing that like that number.
Yeah, but I know Duke Energy, like, being a former employee there, I know how many use cases you guys work with, and it's different for each one. So yeah, definitely understand. All right, so moving on to another question here, or rather a comment, I guess, from Francisco Berman. The AC coupling is really the most common that are seeing in the market, but are there some advantages of using DC coupling for augmentation plans? And that's, I'll open it up to everyone for this one.
Yeah, I
Looks
mean,
like Robert
I
has a
can.
slide on this.
Yeah, I was gonna say I can probably take a stab at it. So I guess we're looking at space utilization. I feel like you're better at using, since most of our projects are land constrained, we have that to think about when we are planning our projects. I guess DC augmentation style can be, you can really optimize, since they can be modular, you can really optimize the space that you're going to use for if you're using DC augmentation strategy. So that's definitely an advantage. The derating of inverters is another thing that you don't have to do compared to AC augmentation, where the initial installed inverters, if you're adding more inverters, the other inverters would need to be derated to maintain the capacity. So DC augmentation basically offers you to use the full potential of your inverters. So that's one big bonus for DC augmentation. And efficient utilization of your megawatt hours, right? Whatever you purchase, you can really squeeze out all the value from the megawatt hours installed compared to an overbuild strategy and an AC augmentation strategy. So I think those are some of the advantages that I can think of.
All right, and I guess, I'll just add to this point. It's heartwarming to kind of see that comment from Francesco, as kind of, relaying my own opinion here. It's very DC augmentations are very worrying to me as an energy storage engineer, right? There's just a multitude of risks associated with the different types of DC augmentations, right? You have form factor risks between old strings slash racks and new racks. You have voltage profile risks. So assuming that you're not going to be paralleling old and new racks, which is kind of the first rebuttal that the champions of DC augmentation will mention, that, oh wait, we'll move all the old racks behind a single inverter and all the new racks behind, a single inverter. That's there's a very dangerous assumption there, in that you're assuming that all old racks have seen the exact same cycling over, whatever number of years the project has been operational, which if you've ever operated a battery project is definitely seldom the case, right? You always have one or two or a handful of inverter banks offline versus others that are operational. So with time, the the degradation and accordingly the voltage profile of different rack arrays, battery rack arrays, are going to bifurcate and be different. So assuming you'll be able to parallel one off of each or a couple off of each with each other, I think is a very, very dangerous assumption. So
Go ahead.
Go ahead.
Sorry.
No, go ahead.
I was just going to say, I completely agree with you. And most of the vendors will definitely say, we have a DC-DC converter, which apparently is their talk for like, hey, we solved everything. So, I mean, but that's not the case. It becomes very difficult where you're dealing with different voltage levels, even if you have a DC-DC converter. Dealing with, I think, one of the projects in the past on the DC bus, if you have two different voltages, it just becomes too difficult to control using the DC converters. And when we have asked whether they can give us the control philosophy for the DC-DC converter on how you would manage different charge and discharge currents and different voltages, that becomes challenging for most of them to kind of give a concrete answer. So yeah, I agree with what you said, Sharif. Yeah.
Great. And also another point about kind of DC-DC converters, and you get a lot of integrators that come out with solutions in which the DC-DC converter is already built into the solution from day one. So each rack has on top of it a DC-DC converter. So in addition to the point Robin made about kind of like control complexity, there's also the losses that are going to be associated with that additional kind of power electronics device there. And even more impactful is, in my opinion, it kind of goes against the whole reason you're doing, or you would be doing augmentation, right? The whole reason you're doing augmentation is to defer cost, to reduce the overall cost of ownership of the battery project. So if you're adding a whole layer of power electronics across your system, that kind of, in my opinion, defeats the purpose. You're solving your problem, but you're really creating a solution that is going against the initial problem that you were trying to solve, which is reducing capital cost, right? So yeah, great to see kind of that feedback from Francesco, and also based on our experience, we typically see champions of DC augmentation being the financial folks that are not taking into account these technical risks, because on paper, right, if you don't put a dollar sign on these technical risks, financially a DC augmentation does look very appealing. But once you get into the weeds and really understand what's at stake, then you start kind of shying away from it. All right, a very good one. Very good question there. Any other comments on this one before we move on to other questions? All right, the next one here is from Karthikeya. What is the impact of AC augmentation on existing grid code compliance of the plant? Another important aspect to consider is the plant downtime due to augmentation. Depends quite a bit on the augmentation methodology. So I think Karthikeya is kind of referring to mobilizations and the amount of time, like as you're, for augmentation, the amount of time the facility will be offline until kind of the augmentation cycle is completed. So
Right.
Yeah, go ahead.
Yeah, sorry to cut you off, Sharif. This was probably going to be one of my last slides and kind of feeds into what was going to come on later on. Initially, when we were planning an augmentation strategy for our project, we definitely considered that. I mean, that was one of the considerations is well, there's going to be downtime for augmentation. Not only that, if your cells reach the end of life, you're going to replenish them. So what are you going to do then? There are going to be multiple off times, not only for augmentation, but for cell replenishment, inverter changes if needed. So this is just a representative augmentation strategy that we were kind of building for one of our projects, where the capacity was being built up to the 100 megawatt capacity rather than having 100 megawatts at year zero. So what we tried to do is kind of align the augmentation and cell replenishment or cell replacement with the augmentation, so that we can really have a minimal downtime of the facility itself. It's definitely a difficult optimization to do, because the cell inverter replenishment with the augmentation can be a bit different based on the degradation that you're seeing. So we try to align our downtime as much as we could for this project by kind of aligning these kind of like stop on our facility operations. I hope that kind of gives some insight, Sharif, to that question.
Yep. Yep. Absolutely. Absolutely appreciate that. Right. Any other questions from the audience? Hey, think we're good on questions from the audience based on the presentation. And Robin, this was your last slide, correct?
Yeah, this was the last thing that I wanted to touch on. And I know
if not, I mean, I think we're good on time. So feel free to continue if you have something else.
Yeah, no, just wanted to kind of, I think one of the, I think that was the slide that I wanted to touch on, but one of the things that I wanted to add regarding DC augmentation, and one of the flavors of DC augmentation is rack which is my least favorite, because you're arranging the battery cells to like align with similar cells with a similar state of health and other characteristics, but it's way too intrusive. These you're taking out cables, you're connecting, disconnecting, and like I said earlier, it's a big concern. Mishaps happen, and that could really cost you even more, just so that you want to save some money on the front end. So that's something that we don't tend to consider when we're just looking at the theoretical aspect of kind of strategizing just based on either economics and how it's going to be dispatched and degradation. But sometimes the ground reality, you have to consider some ground realities where you can't just go inside the rack and start, rearranging everything. It just becomes way too complex to do that, especially in this flavor of the DC augmentation. That's one thing that I wanted to put it out there.
Perfect. Yep. 100% agree. All right. So with that brings us to kind of the panel portion of our webinar. And I have a couple of questions here for our presenters. And, this is really for the entire panel here. So first one we have here, what have been the biggest challenges with developing your company's battery project deployment strategy? And when I say deployment strategy, I'm referring to mainly kind of the if you're going, the overbuild route or AC augmentation, or going with one for a certain type of projects versus another. And I'm going to solicit kind of a response from DTE Energy and Duke Energy as well. So Tony, what's your thought there?
Yeah, the first thing that comes to mind is that technology uncertainty. And then definitely, we see the opportunity to kind of see mix between DCAC at least the first couple of years during the project life cycle. But technology uncertainty is one of the main things, and you see me highlight in one of my slides on refreshing the augmentation strategy on a periodic basis. And this is an important step because as we get more data and as the technology evolves, having a software platform where you are able to refresh your strategy and take a look at the different scenarios again on a periodic basis is very important. So it's not like, hey, we use Storlytics. These are the output. This is the recommended strategy. Strategy is going to be applied for the next 20 years. No, it's got to get refreshed on a periodic basis, whether you're using Storlytics or another storage modeling platform. And I always like to take the analogy, if you've been in a coal plant before or worked in a coal plant, SCR, selective catalytic reactor management, it's a little bit similar, and having the experience in that area allows me at least to foresee some of the problems and some of the opportunities when we're talking about battery energy storage, augmentation strategy. The other aspect is O&M, is a new technology. So operation and maintenance, especially when it comes to augmentation. Are we going to have a contractor help us with deploying these stacks and the arrays, or are we going to take it in-house? And if we are going to take it in-house, at what point you take it in-house? So it's a both-way street for us and the developers and the OEMs. We need to learn from them. They need to learn from us to advance the technology, and essentially it's a both-way street, I would say, where we'll collaborate to come up with the best strategy for us as utilities when it comes to deploying stacks during an augmentation cycle. So technology uncertainty, O&M are the biggest challenges.
That's a very good point, Tony. Kind of I think if you're in the energy storage industry, you definitely recognize how fast things change, right? How rapidly the technology changes, be it lithium or new energy storage technologies, long duration or otherwise. It's really, eye-opening to see how fast these technologies are evolving. And as it relates to augmentation, kind of employing a strategy that relies on benefiting from advancements in technologies as your project kind of progresses, rather than setting something in stone at year zero or pre-deployment of the project, I think will definitely pay dividends. I know we started looking at technologies or new battery technologies out there that are really advantageous when it comes to high cycling, for example, like nickel hydrogen or Venu's technology. You can definitely see it being a good option for augmentation if we wanted to, if the need of a project kind of evolves to high cycling post deployment. So, I take that example from my mind and kind of expand it, and it kind of becomes clear to me, the value of waiting and seeing, for lack of a better term, really as it relates to technologies. All right, definitely appreciate that, Tony. And Robin, kind of shifting over to you, what has been Duke Energy's biggest challenges in developing its battery project deployment strategy?
Yeah, I mean, I feel like Tony was pretty spot on. But one of the things that I remember, one of our business developers kind of asked that question to our vendors, is like, hey, are you gonna exist 20 years down the line when we are kind of laying down the plans for our overbuild or augmentation strategies? How bankable you are, or like technology becoming obsolete, like you've planned. But like I said, DC augmentation, let's say DC augmentation strategy, and well, now the technology is obsolete, so you have to work with different technology or different vendor. So how do you work with that? So kind of asking those questions right now when we're trying to figure out augmentation strategies. So yeah, building up to what Tony said is about the batteries and technology being obsolete sometime down the line. How do you work with that? And also you have to keep up with the regulations and compliance requirements. We have the new IBR requirements come in, which has changed some of the strategy on like we have to relay that to our vendors, and I have them in our contracting framework. So that definitely comes into the picture. So you have to keep one eye on all these different changing regulations and compliances. So yeah, just everything what Tony said, but just adding on 2 more points to it. That's what we're kind of considering right now.
Interesting. Yeah, very good point, Robin. Greatly appreciate that.
Mhm.
And I'll just add one as well. There's, we talked about kind of battery technology kind of advancement and how rapid it is, but if you all kind of look at inverters, right? Even for inverters, if you try to get your hand today on a 600-volt inverter, it is really, really hard. It's, if not impossible, because they're all either 1,000 volts or 1,500 volts, and we're starting to see like 2 kilovolts. So even on that front, like in addition to batteries, it's very rapidly changing, and counting on something in the battery industry not changing over the next 10 years is very, very optimistic. So that kind of adds to it. All right, so moving down the list of questions here. So I know for DTE Energy and EPRI, it's kind of still work in progress as it relates to the deployment strategy that they're moving forward with, be it overbuild, AC augmentation, DC augmentation using DC-DC converters, or DC augmentation without DC-DC converters. If I can put it into these 3 very broad buckets, but still, I'll just still ask, again, I know it's still work in progress. Is there one direction you're going into versus another at this point, or do you feel kind of it's still like an equal chance for each at this point?
Second, I would say, I can comment there. We're still in the middle of it. I mean, we're learning a lot as we progress throughout our augmentation strategy, cross-functional team efforts, especially working with the Electric Power Research Institute. And what has been helpful, webinars like this, and benchmarking with other utilities as well, and listening to what others are being challenged with when it comes to augmentation, selecting the best technology out there. I see Robin put out a point today about total harmonic distortion as you add more and more inverters. So we're going to take that into account as well. But we're still in the preliminary stages of identifying the best augmentation strategy for our use cases. And as we identify that recommended strategy, we'll start digging into the details and some of these challenges that are being mentioned here in this webinar.
Very good point. Jacob, anything to add, or Robin?
Nothing for me.
All right. Okay, well, we have a couple more questions here coming in. First one from Rajat Walia. Regarding value stacking, what is the optimal strategy to stack multiple revenue streams? For example, let's assume a 100 megawatt, 100 megawatt hour system. Is it effective to allocate 50 megawatts, 100 megawatt hours for 2-hour arbitrage and use the remaining 50 megawatts for bidding on ancillary services? Could you please clarify this approach and provide insights on whether it makes sense? So, Jacob, I'll start with you.
Yeah, sure. So I should note that using Dervet and it being a price tag optimization tool, it's not necessarily simulating the same kinds of interactions that you would have if you're bidding into a market. So it's not necessarily developing a bidding strategy. It's just showing, okay, well, given perfect foresight, at least within given windows, what would have been the best capacities in order to maximize revenue. With that said, you could probably get some idea on how you might want to bid given what that dispatch profile looks like. So this will depend. Depends extremely based on what market you're in. It can even depend, what node you're assigned. But oftentimes I do see something like a 50-50, like it'll charge at 50% capacity or discharge at 50% capacity and then bid capacity, the other 50% of capacity to ancillary services. That's not always true though. So I haven't done like a specific hour by hour, I guess, aggregation of most common bidding strategies. That's not a bad idea to take a look at.
Interesting. And, as I think about that question, it's a very interesting one. It's also important to kind of take into consideration whether or not you're planning for these different portions of your projects to execute the two use cases you mentioned simultaneously, or are you planning to kind of have one deployed at one time versus the other, or one prioritized over the other? So you can look at it from kind of a revenue standpoint. But once you're done with the revenue part, you then kind of have to like simulate the actual profile itself, which you're able to do here within Storlytics with either stacking the use cases. In that case, you're able to have in your example 50 megawatts executing a schedule, and the other 50 megawatts, for example, charging from solar and discharging that energy later. So like I said, one way to do it is to stack, which implies simultaneous operation, versus priority, which if the two of them need to be deployed at the same time, it'll prioritize based on this priority list here. All right, very good question there. Appreciate it, Rajat. Moving to the next one here. What are the biggest differences in augmentation considerations between large-scale grid-tied and smaller sites? And Robin, I'll go ahead and start with you.
Yeah, that's a very interesting question. So it depends on, well, if you go with, let's say you're augmenting smaller sites. Now you don't have a lot of modularity right now. If you're just talking about AC augmentation, if you're working with a central inverter, the augmentations might not be very optimized. I think we can look at it benefiting if we have more modular solutions. But more often than not, what we are seeing is like for smaller sites, it's just easy to overbuild because you can justify the funding. It's easier to get that initial capital as well. So why not just overbuild and have the full capacity at year zero rather than augmenting it? For bigger sites, you can have that deferred capital as an advantage with really big sites where you need to provide that justification for getting that initial capital, and in the long run it might be even beneficial doing the AC augmentation. But yeah, right now I think Duke is, for smaller sites we're just going with the overbuild strategy over augmentation, just for that.
Thought you were going to say something, but maybe wrong.
I was going to add to it. It also kind of depends on the application. So let's say for distribution, you're doing a microgrid application, right? So at that point, there is a certain amount of megawatt you will need from the site. So that definitely means that you have to start with that much megawatt. So that by default goes to kind of build up to that capacity. You have to have that capacity available throughout the project life. And then the question becomes, do we do overbuild or do DC augmentation, right? So because of the risk and everything talked about for DC augmentation, overbuild kind of becomes an automatic choice there. And of course, the larger projects, the use cases are not that much definite. So people wants to have flexibility depending on the grid needs. Some of the use cases of maybe now and ancillary services are looking more lucrative, but 5 years down the line is going to shift more towards energy arbitrage. So those obviously has more flexibility around the use cases compared to smaller projects where you're solving for a specific problem.
Yeah, that's a great point.
And really, kind of if I go as it relates to this question, Sanjay posted another question that I think is just relevant to answer this one, right? So how would you go about estimating non-equipment related costs? So in non-equipment related costs for augmentation, so things like mobilization, cost of downtime, recommissioning, retesting. So before getting into that one, just to answer the prior one, for smaller projects, whatever that cost is or how you estimate it, you can be certain that the percentage of that cost as it relates to the cost of a smaller project is much bigger than relating it to a larger project, right? So if you're planning to augment a 5 megawatt hour project, right, it's probably going to be like, definitely more than 10%, or I don't know the exact percentage, but it's definitely going to be more than that percentage for a larger project, right? So that's one of the reasons I think that the Duke Energy approach of not planning to not augment for smaller projects or doing an overbuild for smaller projects is probably makes sense. The other point is really why are you augmenting in the first place? You're augmenting to defer capital investment. So naturally, for smaller projects, that capital investment is not really that large to begin with. So, it's unlikely for it to kind of be an issue from that perspective as well. All right, now trying to address now Sanjay's question, which is, how do you estimate non-equipment related costs when it comes to augmentation? It's a really important one. In fact, I know Jakir and I were discussing this, a couple of days ago. How do you really kind of come to that value? Does it relate to the energy capacity of each augmentation? Does it relate to the power capacity, or is it just a fixed kind of dollar value you assume? So I want to put that to really everyone. And Tony, I'll start with you.
Thank you, Sharif. As I indicated, our effort is a cross-functional team. So we've got individuals on the team that are project managers, project engineers, cost estimators, project developers, that this is their bread and butter kind of things to try and get us the right dollars per kilowatt or dollars per kilowatt hour required for at each augmentation cycle. We also, like I said, we leveraged EPRI. EPRI has a lot of publications, a lot of work that they've done on cost and performance estimations when it comes to lithium-ion technologies and other technologies, whether in Program 221 and whether in Program 94, that helps us validate, some of the assumptions that we're going with, and also, having the Storlytics folks out on the call as well and helping us as part of the cross-functional team. The velocity program that we get when we purchase a license will truly help, because obviously, you have your own database as well in terms of cost when it comes to augmentation or deploying energy storage systems. So a mix of all of that will help us, I believe, get to the right number. And as we go through our first experience, it's very important to refresh the model again. Take a look at your currents versus estimates that you came up with, just refine, reiterate, and refresh your model and see how it looks as you get more data.
Absolutely. All right, Jacob, any response to that, or go ahead?
I think Tony said it perfectly. Yeah, it's a bunch of different sources that we're drawing on to try to align with the correct costs. Yeah.
Absolutely. Okay, Robin?
I'm gonna wait for their paper to come out, to be honest.
Playing it smart. Playing it smart. Like,
yeah.
Nice.
Yeah.
All right. Well, thanks, Robin. Well, that brings us to kind of the end of this webinar. Really, really great questions from the audience. I want to go ahead and thank the presenters. The amount of brain power on this webinar is kind of overwhelming. So really, really want to thank each and every one of you. You could tell there's a lot of brain power on this webinar from the introduction section and reading through the bios of presenters. So again, thank you for being on here and sharing all your lessons learned and experience as it relates to augmentation. And thank you also for the audience, and we'll see you in another Storlytics webinar, hopefully pretty soon here. Our next one is planned in September, so hopefully we'll see everyone then. Again, thank you everyone, and have a good rest of your day.
Thank you.
Thanks, Sharif.
Thank you.
Thank you.
Thank
Bye.
you. Good talking with you all.